Thank you, everyone, for joining the Summer 2022 WebGL and WebGPU Meetup. During this meetup, members from WebGL and WebGPU will give updates on their latest developments, plus we'll see demonstrations from Primal Pictures and Wonder Interactive. First, a couple of housekeeping items. If you have any questions during the presentations, please ask them using the Q&A feature located on your Zoom toolbar at the bottom of your screen. We are recording this meetup, and we'll share the link along with slides when they are available. At the end, please complete the short survey form to help us better design future events. Today, we'll hear from Ken Russel, chair of the 3D Web Working Group, to give an update on the latest from WebGL. Following Ken, Corentin Wallez from Google will give an update on WebGPU's latest developments. Following that, we'll hear from Simon Barrick from Primal Pictures, who will cover fast mesh deformation. Following Simon, Wonder Interactive's Alex St. Louis and Robert Steward will discuss progress in bringing top-end games to the web and demonstrate Unreal Engine running on WebGL 2.0. With that, let's get the webinar started with Ken Russel, chair of Kronos's 3D Web Working Group. Ken?
Thank you, Jeff, and hello, everybody. Welcome. We realize full well that you aren't watching the Webb Space Telescope images being released today in favor of attending this webinar, so we really appreciate your presence. Let me get our slides up. How's that looking?
Great.
Oh, super. All right, let's dive right in. So here is the WebGL portion of the introduction. The first thing that we would like to encourage you to do is please join both the WebGL and WebGPU communities. We say this every time in every webinar, but new people rotate into these every time. So both APIs are supported by vibrant online communities. And if you're using the APIs, we would love to hear from you. So on the WebGL side, you can, by the way, access these slides with the short link in the upper right, and they'll also be sent out later. But you can click any of these links in the slides. There's a WebGL developers list, which is you are absolutely welcome to use for anything related to WebGL. Announcements of products, demos, etc., job postings, please, everything's welcome. Kronos's own public WebGL mailing list hosts lower traffic spec announcements. And you can actually chat with us live on the WebGL Matrix chat room. It's a great way to get directly in touch with browser implementers, raise your bugs or concerns. Just yesterday, a point rendering bug came up, and we were actually able to diagnose that basically live with the developer. You can also find a lot of cool stuff by searching the WebGL hashtag on Twitter. On the WebGPU side, if you have feedback on the API, please see the main WebGPU repo for options on how to communicate it to the community group. The WebGPU Matrix chat room also lets you get in touch with us live and air any concerns or questions that you have about the API. And there's also an increasing amount of cool stuff showing up on the WebGPU hashtag on Twitter. So we are all looking forward to hearing from you. Now let's dive into some browser implementation updates. Firefox has made some progress implementing WebGL extensions, in particular the draw buffers indexed extension, which is used to more efficiently render physically based materials, in particular for GLTF. And display P3 support, wider color gamut support for WebGL canvases, is implemented on macOS and on Windows. In WebKit, several more extensions have been hooked up, including normalized 16-bit per channel color textures, the BPTC texture compression family for desktop Macs, and also draw buffers indexed. Additionally, the base vertex base instance extension and its multi-draw variation are now available behind a flag, which is very exciting because now you can get these and test them without them having been officially ratified by Kronos. There's also been progress on the GPU process implementation, moving the GPU calls out of process from the JavaScript process, and also some cleanup and bug fixing in the extensions related code. There's been fixes to the automatic back buffer clearing after compositing in the browser, and also Canvas developer tools. And I'd like to send a personal thanks to WebGL Working Group member Alexei Knyazyev for these and for exposing the extensions mentioned above. On the Chromium side, we've also been doing work on WebGL extensions, in particular a performance test with Ivan Popelishev from the Pixie.js project to motivate the base vertex, base instance extension, and the multi-draw variant. We're also working on shipment of Engle's metal backend on macOS. There's an ongoing collaboration with Apple, and they've fixed several key bugs. We're working on dual GPU support in Chrome with the metal backend for higher-end, older MacBook Pros. We've raised several limits which were lower than in the OpenGL driver, and we've also diagnosed and are addressing GPU resource consumption performance issues that are sort of blocking shipment at this point. Wide color gamut support for WebGL is out per the Canvas color space proposal, thanks to Chris Cameron from the Chrome team. And we've also been going through several customer reported issues, including, I'm afraid, some security bugs that were found by fuzzers. So the academics who are making increasingly advanced graphics fuzzers are doing a great job. You can test Chrome on top of Engle's metal backend today, and here's how to do it. I'm not going to walk through all of this. But please do test it in Chrome Canary. We would really appreciate if you're on macOS, your feedback on how well it's working. We have seen that most content runs faster in the metal backend. There are a couple of performance regressions. They're unexpected, and we're looking into them now. You can report bugs against both Chromium and WebKit via these instructions. And we would really appreciate, again, your feedback here. So just to reiterate, this code has already shipped on iOS and macOS in Safari, and we're working on shipping it in Chromium. And to reiterate, in case this is the first time you've been to one of these meetups in a while, you can consider WebGL2 to be universally available across browsers, OSs, and devices. And as an app author, you can target WebGL2 with confidence. This revision of the API has resolved many corner cases and behavioral difference compared to taking WebGL1 and adding in the plethora of extensions that were defined for it. So I personally encourage you to migrate to WebGL2, and you don't even need to maintain a WebGL1 fallback path unless you have to reach absolutely every device. And I'm talking about older Windows devices and Android devices. We'd like to point out that many new tests are flowing into Cronus's WebGL conformance repository. These have been discovered recently through many means. Code inspection, investigation of failing tests, work on Engle's metal backend has actually driven a lot of these and others. And I'd like to call out a thanks to Greg Tavares from Google, and once again, Alexei Knyazov, who's independent, for these improvements. And these are going to enable a more portable WebGL2 ecosystem across all browsers. Now, a few quick words on WebGL extensions. The draw buffers index extension, again, this allows you to control things like the blend equation, the color mask, etc. per channel, and is used to enhance the efficiency of physically based rendering. This is already shipping in Chrome. The code has been integrated recently into Safari Technology Preview, so it should come to Safari soon. If you see any bugs in the implementation in either of these two browsers, please file a bug. On Chrome, it's crbug.com, and on WebKit, it's bugs.webkit.org. See the earlier slide. The base vertex base instance extension and the multi-draw variation provide control of these hardware features. And they allow you to reuse index buffers to draw multiple different geometries from the same set of vertex buffers. And they reduce CPU and memory overhead in certain scenarios, but we're investigating with Ivan Papalychev in particular that you can actually improve performance of your app as well using these, because in certain instance drawing scenarios, you can actually batch your geometry better. So if you've needed these draw parameters, please try out the extensions and provide us your feedback. You can try it in both Chrome and WebKit nightly by enabling WebGL draft extensions. And once we reach community approval, these will come to all browsers shortly thereafter. The provoking vertex extension is one worth mentioning. This is new. When you use flat interpolation and shaders, you have to precisely define the first vertex, the provoking vertex, I should say, that starts off a triangle's rendering, or a line's rendering for that matter. And in OpenGL, the convention is the last vertex of the geometry, but it turns out there's a performance cost on multiple platforms, including D3D and Metal, for doing it that way. So this extension allows an application to select the first vertex as the provoking vertex, which should actually be more performance across all platforms. So the extension's in draft form now. and we will expect rapid progress to community approval once it's implemented and tested out by app users. So please ask us about this on the chats if you have a particular interest in it. That's it for WebGL. Now I'd like to hand off to Corentin and Wallez for the WebGPU update.
All right, thank you, Ken. So I'm Corentin Wallez. Hello, everyone. And I will present some updates about WebGPU standardization. So as a reminder, WebGPU is kind of a successor to WebGL, but not a replacement. WebGL will stay in the web platform. And it's a graphics API that's in the style of modern graphics APIs. And what it brings is a couple things, mostly compute shaders on the web. That's great for flexibility for a lot of algorithms. It also brings lower overhead access to the GPU than WebGL, and it's a great foundation for future features. The first release will not have all the bells and whistles you might want, but it's a great foundation to build upon to add things like binary-less resources, ray tracing, multi-threading support, etc. So the development of WebGPU happens at W3C. It's done completely in the open on GitHub, and anyone can join and participate. And also a huge thank you to Kronos for hosting WebGPU in this meetup, even though it's done in the different standards body. So thank you. Some updates on standardization. The standardization of V1 is getting to the last phase. We're just polishing the spec. And on the critical path is also adding a lot of conformance testing to make sure browsers behave correctly. The hope is that we can ship a WebGPU V1 spec for V1 in next quarter, but maybe the latter quarter of the year. So on the shading language side, we're on the polishing phase as well. Recent changes where the addition of shorthand types for vectors, there was a common pain point from developers having to type difficult vector types. There's also been a lot of improvements on the uniformity analysis based on developer feedback, and I'll get to that later. And also lots of polish. API standardization is also in the polish phase right now. What we did since last time was there's been a lot of improvements on the Canvas APIs. So Canvas support is now complete in the spec with color space support. Resizing is behaving correctly now. The alpha mode also works correctly. All of that. So the Canvas part should be about final. There was also the addition of a GPU adapter info that you can query for a GPU adapter that you get. And this is kind of a replacement of the WebGL debug render string. However, it's much more in control of the browser because there's some fingerprinting concerns. And so, for example, the browser might want to ask a permission or just deny getting this info altogether. It's way more in control of the browser. There was also some ergonomics with some reflection and stuff. But again, in the polishing phase. In terms of implementation, there's two implementations you can try today. So in Firefox, if you download Firefox nightly, you can set that preference to true and then start using WebGPU in the browser. However, the implementation in Firefox is not yet completely secure yet. So please don't use that option when you're browsing the random web, only for stuff that you trust. In Chromium, there's WebGPU support on Windows, Chrome OS, and Mac, and other OSs are coming later. And you can actually use WebGPU securely. So we have this thing which is kind of like an open beta called an origin trial, where you can publish websites today that will turn on WebGPU on the user's machine by adding some meta tag in your website. It's expected to go until M107, which is, I believe, the next Chrome milestone or the one after. And it's supposed to cut after that, but we're going to request an extension. So hopefully you can use the origin trial for still quite some time. There are breaking changes. in the API and the shading language, even though we try to minimize them. So please, if you develop WebGPU content, look at the DevTools console and fix any warnings that you see, because they're going to be breaking changes at some point. All the information for the origin trial is on web.dev/GPU, so please check that out. And finally, Chrome aims to ship a V1 of the implementation of WebGPU at the same time as there's a V1 of the spec, so hopefully this year as well. And so what's great with both Firefox and Chromium supporting WebGPU is that the implementations are almost interoperable right now. So there's a lot of WebGPU websites that can work on both, and that's great to see. Next, I'm gonna go on a couple highlights for WebGPU, and the first one is a highlight about uniformity analysis to try and give a brief idea of what it does, but also is to show that like your feedback matters to the WebGPU group, and if you do have feedback, please bring it. So the uniformity analysis is something kind of novel to the WebGPU shading language. It's static analysis, you could think of it this way, that ensures that any gradient or quad operations that you do or barriers in compute shaders are done in uniform control flow. The reason it does that is if you do quad or gradient operations in non-uniform control flow, you might have some of your fragments that are not part of the quad, or some fragments of the quad that are not active. And so the data you would get from derivatives or gradients is garbage. Likewise, in compute shaders, if you do a barrier and not all of the invocations are active, you might get into a deadlock where the invocations wait for the ones that aren't active, and that's kind of bad. So there was a first version of the uniformity analysis in the spec. And if we look at this example on the side, that's kind of standard alpha testing shader, there would be a problem. So we start in uniform control flow, and we sample from a texture to get the albedo for our mesh at that point. And then we do a control flow on a non-uniform value. So inside the if, we're in non-uniform control flow. There might be some fragment shaders that don't get there, and we do a discard. Previously, the semantic of discard was that the invocations that reach the discard are just terminated. They don't exist anymore. And so that's a problem because after we exit the if, some invocations might have been terminated. And so we're now in non-uniform control flow. We were degraded from uniform control flow to non-uniform control flow. And if later we try to sample the specular map, for example, well, that's disallowed, or at least not with an implicit gradient, because you're in non-uniform control flow. And that was a massive problem. It was really like, that was feedback from Babylon.js that they could basically not rework their shaders to fix that, and it makes sense. So the fix was to change the semantic of discard to align with what D3D11 and Metal do. So the semantic of discard was changed to not say that the invocations terminate completely, but that they become helper invocations. And that's actually what a lot of GPUs do on the border of triangles. So the helper invocations, they still execute, they still compute values, but they don't have any side effect. They don't write to the frame buffer or anything. But because they still execute after the if this time, we're in uniform control flow. And so alpha testing written as you would usually now is valid for the uniformity analysis. But again, like what was really important here is that we got clear feedback from Babylon.js that this was not workable. And so we were able to change the uniformity analysis to allow their use case. Another thing I'd like to highlight is the breadth of the WebGPU software ecosystem. And there's a lot of things you can do with it. There's a lot of components. So last meetup, Kelsey showed the shading language tooling side of that ecosystem. But this time I'd like to talk a little bit about the API portability ecosystem. What's great about WebGPU is that the components implemented, the components that are used to implement WebGPU are libraries that you can use in your code. So the library that implements WebGPU in Firefox, it's called WGPU, and it's a Rust library that Rust applications can use. And so if they use WGPU, first, it's easier to use than some of the modern APIs, but also you get portability on all the APIs that WebGPU supports in Firefox, so like D3D, 11.12, Metal, Vulkan, OpenGL. And that's cool in its own right. But now if you compile your Rust application to WebAssembly, there's built-in support for that in WGPU, which will turn your Rust application into a WebAssembly module that uses the WebGPU API in JavaScript, or WebGL in their case. So you can test or run your application in native against all the APIs, and then you can do WebAssembly magic, and it works in WebGPU. The same thing is true for with Chromium's library that implements WebGPU. So it's called Dawn. It exposes a C and C++ header for WebGPU. So you can write a C++ application that targets Dawn, or Zig, or other bindings that targets Dawn. And that in native can work on a variety of backends. But if you compile your application with Emscripten that has built-in support for that WebGPU header, then automatically your application will use the WebGPU JavaScript API. So you can develop in native mostly, and then compile for WebAssembly, and hopefully things just work the same way they're supposed to. So that's one thing for the ecosystem. But now let's say you're doing JavaScript. What cool part of the ecosystem is there? Well, you can use WebGPU in JavaScript without the browser. There's a lot of reasons you might want to do this. Automated testing of your applications on servers and CI with software rendering. You could do offline rendering with the same tech stack that you use to show users things. It's also useful for native frameworks that use JavaScript, like Electron or Babylon Native, etc. So, like, there's two libraries that implement WebGPU in native. There's two stacks there. The first one is Deno, which is a JavaScript runtime, which is kind of new, and it has built-in WebGPU support using WGPU. For Node.js, there's a work in progress module that uses Dawn internally, and that's maintained by the Dawn developers, that lets you use the JavaScript API for WebGPU in Node by just doing import dawn.node if you have dawn.node built somewhere. The state is a bit more work in progress, but it's fairly good. It passes a lot of tests. So, I mean, if you're interested in this, please reach out. Now with the Chromium hat on, the Chromium contributors are making sure the ecosystem works for some of the like bigger libraries in the WebGL ecosystem. So we're having like regular contact, etc. For example, 3JS is implementing WebGPU support, though it's not yet complete. Babylon.js WebGPU support is complete as of their last release, I think. On Google side, we're also working on other like non-rendering stuff. So Intel is working with TensorFlow.js to do WebGPU port with great performance. Google Meet is looking to use WebGPU for some effects and other things to speed up its processing, and a subcomponent media pipe is also targeting WebGPU, etc. And a new thing is that PlayCanvas has started to do a major refactor of the engine to be able to support both WebGL and WebGPU. So that was like personally very exciting to me. So you can follow that on the tracking bug, and it's available. It's not yet available for beta testing, but you can follow that bug. Finally, there's a lot of resources to learn more about WebGPU. Here are a bunch of tutorials that Kelsey already showed. A new one is the article by Surma, which was really amazingly good. So please check that out if you're interested. There's also a bunch of WebGPU samples. The source code is on GitHub. You can play with it. They should be integrated, the best practices. So check that out as well. And finally, if you would like to contribute to WebGPU, there's many ways to do that. The first thing, again, is to try the API and like give feedback on any channel. So it could be on the WebGPU standardization repo, by email to some of the WebGPU implementers, on the Matrix chat, etc. You can also publish websites that use WebGPU, either your own code or using some of the support in some of the frameworks. And you can have users use WebGPU with the origin trial. And also, if there's on the critical path for V1 is the conformance testing, as mentioned earlier. So if you are interested in contributing directly to that, it would be also super helpful. There's a lot of things to do, and any help is really appreciated. And finally, like anything you can do around WebGPU sample demos, articles, etc., would be great. And with that, that's it for the WebGPU update. And I'll give it to Sam and Barrick from Primal Pictures. Thank you.
Thank you, Corentin, sorry. Just switch over. Okay, hopefully you can see that. First off, apologies for the overly long title, which is quite a mouthful. I won't even attempt to read it out. But really what we're talking about here is just a novel approach for vertex displacement, which we implemented as a feature for doing animation in WebGL. I'll go into some of the details of why we decided to use a different algorithm from some of the standard ones, mostly for historical reasons, but in doing that, perhaps opens some ideas for doing other implementations. Start with a bit of background on us and our company. We're Primal Pictures, and we've been doing medical and anatomy, animation, illustration, and products for 30 years. You can see one of the screenshot from one of the products here. So we do very detailed anatomical models. This was all originally built from the Visible Human project and goes into incredible detail. This is just a kind of overview shot, but we go down to, we've done micro CT of the inner ear, and you know, we go down below millimeter scale all the way up to gross anatomy. So we have a very complex data set that was built a long time ago, wasn't optimized for web, and certainly not for WebGL. So we have a bit of a challenge there to be able to bring it to the wider public on a sort of GPU implementation rather than an offline rendering process. So this is what really motivated having to sort of look at some ways to optimize things. We started work on a project that was a functional anatomy project. So we can see a brief animation here. This is grabbed from Chrome. It's implemented in Unity. And very pleased to hear that WebGL 2 is now considered sort of standardized, because this whole system relies on it being able to use WebGL 2. It won't run in WebGL 1 at all. So we're looking at human body. Later on, I'll show some other shots of where we zoom in right onto the hand, and there's a lot of smaller stuff going on. So we have to deal with very different set of scales, from large gross anatomy down to small, very small stuff. And it's, as I say, the mesh isn't necessarily optimized for you know, fast real-time rendering. You're seeing nearly 2 million triangles represented here, of which about half of them are animating, actually deforming, I should say, as well. So we had to come up with a way of being able to run all that in a browser, which is really what we're talking about here. So it was kind of an engineering challenge. I won't go into the real details of the implementation, but if you obviously want to know more, you can reach out to me, and there'll be more details. This presentation will be available on the Chronos website afterwards, so you'll be able to see a little bit more about it there if you want to know more about the maths. There's a few slides at the end that cover it, which I probably won't get to in this presentation. That delves into it. It's basically implementing or re-implementing some old ideas that come from RBF, which some of you may be familiar with, and I'll just sort of go over some of that, sort of how it's traditionally used to start with, and then how we modified it. So being for web delivery, obviously we need it to be fast to download, and we target our customers are students quite often. They're not necessarily on the latest hardware, although a lot of people have high spec Macs, not everyone does. So we need to be able to keep this as small as possible and run as fast as possible on every piece of hardware. So that was the challenge. Here's another little demonstration. So this is currently running, although the screenshot there shows it running about 47 FPS, it runs at 60 FPS if you're not doing a screen grab at the same time. But on desktop, it runs over 200 FPS. So really hopeful that WebGPU perhaps lets us grab a few more frames per second out of this once that's implemented. And possibly even with compute shade, we'll be able to actually do the deformation directly in real time. This is currently an offline process where we animate first and then store the animation to play back in the browser. So a few stats there, about 500,000 triangles that are animating, and 250,000 of those are actually deforming at any one frame. So existing solutions, how could we have done this? I'm sure a lot of you are aware of the normal kind of approaches to this. You can do an image cached vertex deformer, where you basically take every vertex and stuff the position into an image, and then just run that through a shader, put it through the vertex phase, and just play back that animation. That's one approach, which is great if you're trying to capture a really detailed, let's say a simulation, like a water simulation or something where you've got something very complex, then you need absolute precision. And the other approach is bone capture, where you have a much sparser capture system, and you use bone deformation to play it back. But then you lose some of the accuracy that you would get with the point-based one. So yeah, a few little overview here. The nice thing about image caches is they're simple to implement. They're really fast. They're accurate, because you're literally storing the point position. But you have quite a lot of large amount of data to download, which is obviously negative when you're running in the browser. And you need to store both the point positions and the normal positions. There's some benefits to the bone capture, as I've mentioned. It's sparse, which is nice. We like that feature. It's a little bit hard to get an accurate capture. You have to do lots of analysis on the captures, see where the errors are, move the bones around, try and find an optimal position for them. All of that takes quite a lot of time to set up. But again, it's still pretty fast. We're just doing some interpolation, which is all built in now, obviously, to the engines. All of our stuff is actually developed in Unity, and they have their own bone implementation that's pretty fast. But again, you've still got a fairly large amount of data. But really, the downside to bone capture is the accuracy, and the downside to the image solution is the amount of data. So we wanted to kind of blend those together, try and find a better approach. So we want to keep the image-based side of it, so we can just run it in a fast vertex shader on the GPU. We want it sparse, so it's independent of the mesh that's being animated. We need it accurate because we've got all these different scales that we need to deal with. So the solution we ended up with, it's just one matrix multiplication per point, which is pretty nice. It's not a lot more than what you're doing for the image cache. So it's pretty fast to run. And then we calculate the normal once it's deformed rather than storing it. So that's similar to the bone method. There's a minimal amount of data to download because it's sparse. We actually end up with anywhere between 2 and 10x improvement in the amount of data that we're having to download. It works best for the type of animation we're doing. So if you had you really needed every single point to be in a very precise position, then it probably wouldn't be the best. But because the nature of the animations that we're actually dealing with, the smooth transitions actually store very nicely. And in some cases, we can store a whole structure being deformed in 5 or 6 points. So it's completely tunable on the amount of data that you want to store, depending on the animation. And the only other additional detail is that it requires a UV set, an additional UV set that's used for the lookup process, but that only needs to be stored once. So you only need one mesh with one set of UVs, special set of UVs. So a little bit more into the actual details. So it's an RBF solution, so radial basis function, but we've broken it up into a piecewise formulation rather than doing the whole thing at once. So traditionally, you would have a set of feature points, and you would map those feature points to a set of target points. And through a set of linear equations, you can solve that out and end up with a set of weights to apply to map your source mesh to your target mesh. That's great, but then you need to store that entire set of target points. But by breaking it down into patches, we can actually simplify this a lot. And the other thing that we we note is that if we break it down into small enough patches, the actual weights themselves that are calculated through the RBF function, they all disappear to zero. And basically they become an error feature. So if the error is small enough, you can ignore it. And what you end up with is just a transformation from the target patch to the, from the source patch to the target patch. So in this illustration here, the green dots are the actual mesh that we want to deform. So as I said before, it's not particularly optimized for web. The blue points are the source points. So we specified it basically. And then the gray mesh is just an illustration here. It's not actually part of the calculation, but just to sort of illustrate what I mean by a patch. So around each feature point, we can select up to any number really, but we use sort of 6 to 12 works reasonably well, other points to create a patch. And then the calculation works out a transformation that moves that patch from the source to the target. And then where the two ultimately don't match, those weights are really just considered errors, and we just ignore them because if you tune it so that the feature points are in the right place, you just need the transformation, which is really the crux of this approach. So we calculate the RBF, which is just a solver. It's just a standardized solver. All of this is available through Google. You can just go and look up how RBF works. You can create a set of linear equations that you just solve with a matrix solver. And then, as I say, because the weights are all zero, we just chuck them away and we end up with a transformation. That transformation is basically transform one patch to another, and we can store that in an image. And then for each of the green points, we just store the index of the source point as a lookup. So we can then look up that UV position in the image in order to perform the transformation once we put it into the deformation shader. And that's really the crux of it from a high level. As I said, we recalculate the normals after we've done the deformation. We don't store them. And you can just offset each individual mesh point along its tangent and bitangent and do a cross product, and that recreates the normal once it's deformed. So that's similar to what you'd do with bones, although that's all built in, obviously. Quick note on how we specify the points. As I say, that the source points can be anywhere on the mesh, but if you need more detail in a particular area, as I'll show in a minute, in the situation of the hand, there's a lot of very tiny structures and they have a lot of points in them, and we need our feature points very close together. In something like I showed earlier, where you've got very large muscles, those feature points can be very far apart. So just as you would with bone capture, you can just distribute them around. And it's very easy to calculate the error and see whether or not you've got enough points, and you can just add points where you need them. There's no need for connectivity. You just scatter the points on the surface. They can be anywhere. So we end up with a kind of combination of a bone system and a cached image system, but we don't need to interpolate between like 4 bones. We just have one single transformation for each patch, which is applied to every single point that's got the index for that patch. So that's super fast. And we have a small amount of data to download because we only need the transformation values for the source points. So they're quite sparse. So just another quick demonstration. This again, running in Chrome, built in Unity with WebGL 2.0. So that's really the crux of it. As I say, there's the slides about the actual implementation. I won't go into those details now because I'm sort of towards the end of the presentation here, but we can go into that in the Q&A, or if people want to contact me or just look at the slides afterwards. The information is broadly there. Obviously, there's how you implement it is down to you, but the mathematics of it is kind of laid out there simply enough. And finally there, that's just an example of the sort of image that you end up storing for an animation. So for each frame, we do this process of calculating the source to target transformations and then storing them. And I just store them in a PNG file, and they compress quite nicely as well. So that's the end of my presentation. I will now hand over to Alex and Robert from Wonder Interactive. Thank you.
Thanks so much. Great presentation. Can everyone see my screen?
Yes, looks good.
Okay.
Yes.
Okay, so today we're talking about bringing the Unreal Engine to the browser. My name's Alex St. Louis. I'm co-founder and COO of Wonder Interactive. I'm presenting here today with Robert Steward, CTO and CEO of Wonder Interactive. So I'm sure everyone's wondering, what do we actually do? Do we work with Epic? No, we don't. So we're actually a platform as a service and tooling vendor to enable developers to ship native games and real-time 3D applications to the web. And if you look at the state of game engines and web compatibility, it's a bit messy at the moment. So Unity to date has the best support for exporting to HTML5. Unreal has had in the past support for this, albeit not the greatest support. So we're actually solving this with proper dev tools and a hosting platform for developers to seamlessly optimize, distribute, and deploy, and then manage their games on the web, utilizing WebGL currently, WebAssembly, and in the future, WebGPU, which is really going to provide this near native performance and a pretty consistent experience across all devices, desktops, laptops, and mobile. So if you look at the history of Unreal in the browser, Mozilla and Epic actually collaborated back when Unreal Engine 3 was out. So that's 2 engines ago for Unreal. And utilizing a precursor to WebAssembly, Asm.js, Mozilla and Epic were actually able to, in I believe 4 days, get what you see here, this screenshot of a demo called Epic Citadel up and running. And so Asm.js, you were getting really good performance because it's JavaScript. You really wanted something like a WebAssembly, but this was running in WebGL. So now with WebAssembly, Unreal Engine 4 actually kind of continued this, and they started, the team at Epic built out the ability for developers to target WebGL WebAssembly as a platform target. And so WebGL 1 was only supported. The beginnings of WebGL 2 were being built out so that developers could export to the web. However, as you see here in 4.23 release of the engine, so about 7 or 8 releases ago, Epic actually officially removed support for exporting to HTML5 and made this sort of a community supported platform extension. And so at the time, I myself was trying to package a game for the web. And the biggest issue that I found was that the binary size was much too large. You'd be asking your users to wait for a very long time, which on the web, users expect a very instant experience with good performance. Expectations are different on the web than on desktop. So this combined with only WebGL 1 being available, it was a very poor experience compared to engines like Unity or Play Canvas. And that's when actually I met Rob, and Rob was doing work for studios and companies that needed this specialized, unique expertise to bring these real-time 3D projects and games made in Unreal to the web. And so since, we've actually added WebGL support to the later releases of the engine, including ones where they don't actually have it. So 4.24 to 4.27. And this has provided a tremendous performance increase. Yeah, so WebGPU is clearly the future. We're actually building out a WebGPU backend for Unreal Engine 5. We're quite excited about that. And we actually have a WebGL 2. We've migrated our WebGL 2 backend from Unreal Engine 4 over to Unreal Engine 5 as well. We have that rendering. And some of the major innovations that we've kind of served here are We've actually imported a basis texture compression to get file sizes smaller, but mainly on the asset streaming, instead of loading a big monolith of a file up front, and say you have like a 500 megabyte game or 750 megabyte game, you don't actually need all of that all at once, because you might only need, 20, 25, 30 megabytes for the main menu, maybe another 40 or 50 for the main lobby and say an MMO game. So you can actually, utilizing asset streaming correctly, you can actually load upfront what's needed, what the player needs to see, which this is very beneficial for developers because it increases conversion rates and speeds up load times and getting players into, or just users into an experience, say, think like for a 3D showroom, much quicker. So everything else loads in at runtime as necessary. And Rob is actually going to introduce the features of our platform. Are you there,
thanks.
Rob? Yeah.
So, yeah, I'll also mention one other thing. So great points there, Alex, but there's one other thing I would like to mention as well. And it's also with the asset streaming, it's going to enable much larger games as well, which you don't typically see in the browser these days. Especially useful for open world games and games where you're going to travel, where you have many different levels that don't all need to be loaded at the same time. So this is going to enable larger games now, we believe to be common in the browser. And yeah, so we have our SDK, which is basically an Unreal plugin. Well, we're initially targeting Unreal right now. We're working on support for other engines as well, but currently we have an Unreal Engine plugin, and essentially what you do is, for any developers that are working with us right now, since we haven't reached general availability yet, the developers that are signed up right now, though, they go onto the dashboard, they get their client ID, and they put that in the plugin tool, and then they can generate a project on the dashboard, and they put that in the HTML5 settings as well. And yeah, it's actually quite simple. In Unreal, those are the two main settings you need. If you were to go and do that for any of the template projects that Unreal has right now, you wouldn't have to do anything else, and it would upload to the service, and then from there, a developer can choose if they want to make it active on the platform or set it live on another site and such. So yeah, and then we have WonderNet is a set of tools that we're using to take advantage of, it's not so much graphical related, so I won't spend too much time on it, but to take advantage of WebRTC and Web Transport, so that developers can use networking in their games. And yeah, and then we have the dashboard, which I briefly mentioned. So this is for provisioning and maintaining builds, and it's where developers get to see kind of a history and a breakdown of their past builds, how users were using them, the startup times, and stuff like that, so they can optimize their future builds as well. Yep. If you can go to the next slide, Alex.
Okay, so we're going to show a demo now of a game. We actually, well, a small demo of a game, a mini game, I guess you could say. This is running in WebGL2, Unreal Engine 4 4.27 release. And this demo makes good use of our asset streaming technology, as you'll soon see. I'll go full screen here. And so, as you can see, a very large open world with lots of actors present. Lots going on here. I'm going to go through a portal or a warp. And so as you can see, we're in a different level entirely. our asset streamer is doing its job. And what if we want to go to another world? Well, we can do that. There's some ships. And we actually have gamepad support for this as well. I'm getting attacked now. And this is just quite a small demo that our team threw together in about a week. So we're quite excited to see what real indie professional and other game studios and publishers are able to do with this. With WebGPU and Unreal Engine 5, we're quite confident that we're going to enable some of the highest fidelity games available on the web. So we're very excited for that. And I'll actually exit this now. So what's next for us? As I mentioned, Unreal Engine 5, we already have WebGL 2 support. WebGPU support is currently underway. Yeah, we're currently onboarding game developers that are interested in our service. We have a waiting list. We are planning on extending our tools and our platform to other engines. We've started with Unreal Engine as historically, again, it's the engine with the poorest support, but we do intend to support Unity, Godot engine, and also Amazon's open source Open3DE engine. And another interesting point, I know this is WebGL WebGPU, but I'll mention we are building out WebXR support for all of these engines as well, starting with Unreal. So developers will be able to ship these cross-platform VR applications. That's going to be very important for any sort of metaverse experience, having interoperable experiences, no matter what device you're on. And we're very excited to help build the immersive web, the 3D web. And if you've ever used Unreal Engine, if you're a developer, if any of this has interested you, if you want to just ask us some questions or chat, we have a Discord community. You can also sign up for our platform and early access to our tools at theimmersiveweb.com. And thank you very much.
Thank you, gentlemen, for the cool demonstration of your platform. That was neat. Next up is the Q&A portion of the webinar. If you have any questions, please submit them using the Q&A button on the toolbar at the bottom of your screen. Ken Russel will be moderating this panel. Ken, take it away.
Thank you very much. Awesome work, everybody. These were just great presentations. Actually, let me take the liberty, since I can't actually post questions. Alex, what was the local frame rate of your demo? Because the video conference software made it deliver only a few frames a second here.
Yeah, that's a good question. So that was actually a shipping build of that demo. So if we did a development one, we actually could toggle in the console, the Unreal console, in Chrome and see what the frame rate. My estimate would be probably like mid 30s, high 30s, perhaps 40.
Let me
Go
scoot in there.
Go ahead, Rob.
So on unless your desktop's really underpowered, Alex, that should be capped at 60 frames per second. On my desktop, it's capped at that, but yeah.
Okay, super. I mean, I'm sure we're all looking forward to playing it live. It looks great, just great.
Thanks.
Okay, so why don't we go down in chronological order here? I think the first question is probably for Simon. How does potential floating point imprecision get handled in your RBFs?
Yeah, that's a really good question. So there's two aspects to that. One is that for each animation captured, we shift everything to the origin and deal with it all at the origin. And then there's an additional parameter that just deals with the offset. And then for actually storing the values, there's actually two pixels that are used rather than one. So basically pack the 16-bit float into 2 pixels. I kind of skimmed over that because it's just an implementation detail. You could go up to 16-bit, 32-bit, whatever you want. That's just how you pack it in the image, basically. So that really deals with it.
Okay, super. Oyvind, if there are any follow-up questions, please toss them in the Q&A. Let's see. So Corentin, I think this next question is for you. How confident are we in the Q3, Q4 timeline for WebGPU v1? Because there have been some schedule slips, and I'll just, in Corentin's defense, this stuff happens. I think the uniformity analysis came in like after the initial estimate, and it's been a significant improvement in the portability of the shader aspect of the API. So please.
Okay, so to answer the question concretely, like directly, let's give it a 90% sure it's this year. It's fairly confident, but like stuff happens. Standards are like really tough, and there's an infinite amount of stuff to do. A couple of things on this is like when we started WebGPU in 2017, like it was January 2017. I honest to God thought it was going to take 2 years. So now we're 6 years, 6 years in WebGPU and still in development. So yeah. The other thing is, I think the bar for shipping WebGPU is like super high. Like the feedback we've had is that WebGPU should have basically all the features that WebGL has, and like in more and better performance and everything. And like there's more concerns about fingerprinting, etc. So it's been really hard to tick all the boxes at the same time. One thing we're skipping for V1, I think, is WebXR support, although that's going to be coming like really fast afterwards. But it's just like to give you the scope of WebGPU is massive. So again, like fairly confident, but stuff can happen. We're really trying our best. There's like, as far as we can see, there's only that much work, but there's always unknowns. And like, you want WebGPU out, we want it out like so much as well. It's just there's work to do.
All right, great answer. And yeah, we're all trying to get this this product out the door. It's going to be amazing for the web. Next question is actually about Firefox. We don't have a representative from Mozilla here, but Corentin, do you want to give any knowledge of yours?
Yeah, so like it's hard to answer for Firefox, given like it's hard to answer for somebody else's browser. What I know is that they have a fairly good implementation in terms of like the features. They're a bit behind on spec, and they have like engineers working on it a bunch, like really amazing engineers. So the hope is that they can catch up and ship soon-ish after. Like let's give it 6 months, a year, but like I have much less precision on that answer because obviously I don't follow and I can't speak for Mozilla. So my gut feeling from looking at their repo and the questions they ask, etc., is that, but it's better to just ask them directly. What you can do is ask the question on the Matrix channel, because all the people working on Firefox WebGPU support are in that channel, so they can answer directly.
All right, great answer. Next question is for Simon again. For the blue points that you use, the sparse points on the surface of the mesh, are those generated in a pre-processing pass, or are they generated at runtime?
Yeah, so yeah, another good question. Yes, those are all generated offline, and then we just throw them away. We don't need them. It's only the result of the calculation that gives us the transformation that's stored in the image. And then the UV that stores the index into that image is the only other bit of information you need. So the blue points themselves, they're just irrelevant once the calculation's been done.
A quick follow-up that I think I may have seen in the chat. How do you select the blue points?
Well, so initially, there's two ways I use. I just do a scatter operation, which sort of tries to uniformly scatter them. And then you look at the error and you just go, okay, this bit of the mesh is going to deform a lot. I need more points there. And you can add, there's lots of techniques you can throw. I have a few systems for using the UV values and sort of selecting a range and go put more points there. Or you can even just look at the error and go, if the error is high, put a point there. And then I have another method where I actually use a remeshing algorithm that, because of the nature of the remeshing algorithm, gives a really nice distribution of lots of points where there's lots of detail and not many points where there's no detail. And that gives actually quite a nice, if you have a non-uniform shape, like a lot of these muscles, they're very skinny in one bit and very big and flat somewhere else. So you can have like 6 points on the really big flat bit and 10 points where it's narrow. and the remeshing algorithms do a great job of actually deciding for you where those points should go. So that was quite a good technique that we came up with.
Very cool, thank you. So it looks like the next question is for Alex and Robert. Will your project also support UE5?
Yep, that's the plan. Unreal Engine 5 is going to have WebGPU support. Unreal Engine 5 is still like pretty early days, like it was just released this year. So yeah, we'll be building out this functionality as Epic continues to add features to the engine as well.
Yeah, we have WebGL 2 support already for Unreal Engine 5. And so the developers that come to us right now, we can basically get them set up with Unreal Engine 5 today if they wanted.
Yeah, and with WebGPU, you'll be able to get features like compute shaders. So there's a lot of there's a lot of features that that are gonna be on par with native that you can't do today, that are really going to contribute to these higher fidelity experiences that are really waiting on WebGPU. So we're super excited for those.
Very cool. So actually, it looks like the next question is for both of you as well. Is this a UE plugin? You've
part of
already
it.
answered this in your presentation.
Yeah, part of it is a plugin. The front side. I could go a little bit more into detail, I guess. So there's the plugin, and then that hooks up to our backend. And so we have 3 tiers, right? We have the free tier, which is not active yet, but essentially using that and the plugin, you can deploy to our discovery service, which is the immersiveweb.com. And then studio tier and enterprise tier have more options in how do they distribute, like maybe on their own website, for instance. And yeah, so just thought I'd mention that.
All right, very cool. Another question for you, Alex. How is your platform different from Play Canvas, for example?
Yeah, that's a good question. Right away, I'll say Play Canvas was an engine that was built from the ground up for the web, and so it does a lot of things well that like the native engines can't really do right now. But obviously, I know the runtime is it's pretty, the footprint is pretty small for Play Canvas. Unreal Engine specifically is, it's quite a beast of an engine. So big code base. So there's a lot of rich functionality that isn't present in a web-based engine, because you can't, it doesn't really make sense to do, or it's not possible to do that. For Unreal, targeting the highest quality native experiences on PC, console, although still being an engine that can scale to different platforms, like Fortnite is on I think everything possible. So yeah, I would just say mainly the feature set of Unreal. With Unreal 5, we're going to have Lumen and Nanite, which is going to be a game changer for photorealism in scenes. Rob, do you want to add in there too? Any other points?
No, not really. I think you got it pretty good. I guess I'll just say, yeah, so it's a more it's a big engine with a lot of history, and yeah, aside from what Alex said, that's pretty much it.
Okay, so the next question was hoping for the link to the demo.
Oh, yeah, I can post that in the chat. Yeah, okay. It's play.spacelancers.com.
Yeah, and just give it that's early, that demo is early, so there's no loading screen yet. You might have to give it, depending on your internet connection, up to even a minute the first time. It loads much faster subsequent times. That is one of our bigger demos. We do have smaller demos that can load up within 15 to 30 seconds on a bad connection, and as short as 2.5 seconds, I think, is the quickest we got them to load on subsequent turns. So
all right, startup time is going to be the the biggest challenge with a beast as big as the Unreal Engine, as you know. So okay,
yeah.
Looking forward to your improvements here. So Brandon asks, the stream frame rate of your demo was a bit choppy. Could you point us at a video that shows the real frame rate? Is that going to be in your slide deck that's shared later?
Yeah. Yeah, so I think maybe I should have mentioned that as a disclaimer. I think over Zoom, streaming a video of gameplay, I don't think it translated how smooth it was on my end too, but I'll let the demo speak for itself.
Yeah, and I'll also mention that demo, while not targeted for mobile devices, can actually run on my Pixel 6 phone as well. So we're actually targeting for low-end devices as well. And one of our initial developers targets Chromebooks, for instance, like almost exclusively. So we're putting a lot of effort into getting this to run on lower powered devices, although this demo is specifically being designed for desktops and maybe consoles.
All right, this is cool. I mean, WebGL itself was designed to span mobile and desktop. So it's really encouraging to see that you're able to take advantage of that. And, you know, restrictions in the WebGL API set were designed to allow content that was developed on desktop and tested there to run immediately on mobile with no changes. And we got there, you know, by and large. So this is great to see. Okay, so next question is probably for maybe Corentin and me. Could you paint a picture of how high-level APIs like Three.js would implement WebGPU? Would it need a separate API set?
Forgot to unmute. I like Three.js. I've seen less. I've looked at it less closely, but Babylon.js, they've been able to implement WebGPU support with, I think, a single API change, which is that the creation of the engine is now asynchronous instead of synchronous. But that's the only change they've had to, the only breaking change they've had to do. However, when they do that, they have to do a lot of work behind the scenes to make existing content work. For example, they can ingest GLSL shaders, like custom shaders in Babylon.js. And so they have to translate for the user, and that brings like a whole WebAssembly module translating from GLSL to Wixel. They have to do a lot of caching of the pipeline. So WebGPU asks for a lot more state upfront than WebGL. It's a bit less dynamic, but like more efficient when during the steady state. And so they have to do a lot of caching to be able to keep this state around. And they added like additional APIs to be able to freeze some properties so that they can better give information upfront to WebGPU. So like the idea is that you can basically port your engine as is to WebGPU, except for a couple of things that are asynchronous. But if you really want to take advantage of it, you might need to change a couple of things here and there, like to give more information upfront.
Sounds good and sounds fair. I've had a peripheral involvement with the Three.js port to WebGPU, and that engine is factored with a renderer in the back. So you've got the front-end API, the scene graph API, and a render API, the immediate mode aspect of it. And to the best of my knowledge, the public API hasn't needed to change in order to do the WebGPU port. It's just been entirely behind the scenes. So while there are some, again, asynchronous aspects of WebGPU that aren't there in WebGL, I think by and large, the API structure that is presented to the end user does need to change. But if you do that, you may be able to get some better usage of, for example, bind groups, which might be harder to like infer from the user's scene graph. Okay, next question is from Ali Etsuaho, an alumnus of the WebGL working group. Hi, Ali. He's asking if the demo that you showed is publicly available, and I'm pretty sure the answer is yes.
Yeah, I believe it's in the chat there, play.spacelancers.com. Yeah.
Well, ours is not a WebGPU demo though.
WebGL. Yeah, this one is as visually as impressive as it is. It's just WebGL 2. So we will upgrade it to WebGPU though, for sure.
Sounds good. Sounds good.
Yeah.
Okay. Next question for, once again, Alex and Rob. For downloading game assets, how much are you able to cache locally, and how much do you have to download each time you visit the page?
Yeah, I can answer that one. So
yeah, go ahead.
It's going to depend on the device. So yeah, we have essentially with our asset fetching and caching system, it's able to use multiple backends on the browser for storage. So either the cache API or the I always forget the acronyms, but the OPFS or whatnot, and it's able to store up to, depending on the browser that you're going to run it on, Every browser has different limitations. On desktop, if you've got plenty of hard drive space available, it's hard to give maybe a concrete number right now, but if you have space available on your desktop, chances are it's gonna save, like, we don't impose any limits over top of what the browser has for caching data. If it can't store something into the cache, it'll have to, and if it can't store it into memory for a memory constrained device, then it will pull it from the CDN again. And yeah, so like on Chromebooks, for instance, I mentioned one of our developers has their primary audience is Chromebooks, and they often have much smaller devices with very small caches and compared to desktop. And so, yeah, sometimes, like, for instance, for a game that it might take 30 megabytes to get into this one particular game. It's a sort of MMO. And then that's easily going to fit inside the cache and the memory. But then as they move around and play for, say, an hour or whatnot, most of that's still probably going to be able to persist in the cache, but you never know. On these Chromebooks or mobile devices, it may evict some stuff and then you'll have to grab it from the server again. So it's hard to say a concrete number, I would say, right now.
And just to follow up from that as well, as part of our plugin, we actually have in the settings where up to developers to set the maximum allocation for the storage that they're using for their project. And so you can set the minimum and maximum.
Yeah, so that you can avoid cases where someone tries to run it on a device that you might not be targeting. So we want to have games, like if game developers want to make games that are mobile focused, or maybe cross-platform, maybe it has mechanics that are good for cross-platform. But then also if they want to have strictly high-end desktop games, we want to support that as well. And so they can put that in the settings, put these requirements in place so that so on the front end, someone on a mobile phone is not going to get necessarily directed to that game unless they wanted to try it. They can disable the settings to filter those out. But yeah.
Okay, I anticipate a lot of folks having questions about this. Do you want to maybe join the WebGL Dev and Implementer chat?
Definitely, yeah.
Then folks can come over
Go
there
from
and
there,
ask questions about Wonder. Okay, super.
Yeah.
Yeah. One thing I'll mention is if anybody sees like a white screen at like first load, you can actually, you don't have to, but you can like just wait for it to load. You can also press F12 to open up your console, and you'll be able to see the assets being downloaded. But yeah, we're gonna add a progress bar and some sort of loading screen there. Yeah.
All right, sounds good. Are you going to render the progress bar with Unreal Engine?
Maybe.
Chicken egg problem.
Yeah, possibly. We wouldn't have to, but it's an option. Yeah.
Okay. So next question. Corentin, probably you and I will answer this one. Isn't the increasing adoption of server-side rendering with native 3D APIs somehow a response to how far behind web APIs stand in exposing modern hardware? So I'd like to provide a bit of an answer to this first. The proliferation of very capable GPUs in the ecosystem has been tremendous over the last, decade in particular, since WebGL has been, present on the web. And the fact that you can take advantage of that local graphics processing horsepower with both WebGL 2 and WebGPU is, it's a scalable and democratizing force in the graphics industry. So I would just like to point out that the kinds of applications you can develop with these APIs, like Google Maps, for example, on desktop, has been hosted on top of WebGL for the better part of a decade and has enabled, radically different experiences for in-browser mapping than was previously possible. It's a Figma, for example, a multi-user design application has revolutionized how people are doing design across a range of industries. It's hosted on top of WebGL. It wouldn't have been possible to do without WebGL in the browser. So I think that WebGL, it's had a long lifetime, and we are still going to maintain it, pretty much forever. But WebGPU is going to be the single force that moves web graphics dramatically closer to native functionality. And Corentin, any further thoughts on this?
Sure, yeah, and like from a different angle, actually. So I assume by server-side rendering, here the question is about Stadia and other like streaming services for games and stuff. It's like I don't think it's an answer to specifically the like the state of web APIs. It's a different market. If you look at it, I mean, and like this is me talking with absolutely no experience in this field, but it really does feel like it's a different market. On the web, like you've seen, you have like you pay for, like you have to download the thing, and so you can't like, you need to be a lot smarter in how you cache things, etc., to be able to have good experiences with loading times. You need to make sure your application is portable. Whereas the things that are streamed on these services, they're more like console games that are used to targeting a specific set of hardware that can be like really huge, and they don't necessarily want to like care about working on all the form factors and like all the types of clients. They just want one thing that works well, and they're used to the console environment. So it's just a different market. I really think that with WebGPU and also a lot of the other web APIs that are coming up, a favorite of mine is the web authentication APIs. I'm really looking forward to that. I really think with all these kind of APIs, then we're going to have another ecosystem that can grow in the web with a lot more experiences. It's a different market, and you can have both.
Well
And
said,
I think,
Corentin.
Simon, you raised your hand.
Yeah, it just made me think of a question that we've had many times. Like my laptop is a dual graphics card, so you've got the onboard one and an NVIDIA card. Will WebGPU ever allow us to bury straight through to the more high performance card if the browser is actually running on the native one?
Yes, but that requires, so WebGPU has a thing where you request an adapter, so you can discover the GPUs in the system under control of the browser, of course. And you can request, I don't remember the name, but like high performance versus power efficient or something. And so you could get both GPUs in the system and choose the one you want, and specifically the high performance one. However, support for dual GPUs in browsers is hard for reasons that are not like to do with the APIs themselves, but we need to transfer images back and forth between the GPUs to be able to composite the WebGPU content into the integrated GPU page that's rendered. And because browsers grew organically to use GPUs, this is a refactor that's amazingly hard. We're talking decades of engineering here overall to make that happen. And so it's ongoing, but like on some systems, it might take longer than others to become available. Like talking for Chrome specifically here, other browsers might have it better.
Okay, super. So another question for Alex and Robert. Do you have any WebGPU demos yet?
No, not at the moment. Currently, we're still developing out the WebGPU backend. So yeah, no demos.
Okay, all good. I'm sure they're coming soon.
I think
Yeah.
I think
This
at
summer,
a future
correct.
I think at a future WebGL WebGPU meetup, we will have more to share on that.
Yeah.
All right, super. We are eagerly looking forward to it. Okay, so the next question is a two-parter. I'll leave it open in the Q&A, but first question is, do you need to set the maximum amount of memory in the configuration file the way that Unity does?
You don't, you should. So there's a default, and then you can set a limit, but you don't have to. You can allow the memory to grow as well. Yeah.
Okay, sounds fine. And this one is maybe a more open-ended question. Maybe we should let that one go to the WebGL Dev and Implementer chat. But any experience debugging memory crashes in WASM and how you debug them?
Yeah. So just briefly on that one, then we have. So there's basically. We don't have any like specific tools outside of like the Chrome dev tools for for like debugging these things necessarily. We try to admit proper errors when it's maybe if the wonder, maybe if you're exhausting the memory, for instance, that's one thing that we can let the user know and the developer. But yeah, so for debugging these things, we use Chrome dev tools. And that's what developers can use as well if they're hitting crashes, memory crashes.
Cool. Corentin, you got your hand up.
I just wanted to mention that in the last couple of years, the Chrome DevTools gained a lot better support for debugging WebAssembly, where they're able to load debug info files and show, line numbers, local variables, and other stuff. So, I don't have a link offhand, but I know there's articles on the internet on how to do that, and please give that a shot. It's pretty good. Yeah,
and we use that. I'll also mention on larger binaries like Unreal, it can because the binary can be, well, if you're doing a development build, it can be over 200 megabytes sometimes. So it does work though, but as long as you don't accidentally navigate to the WASM executable, which it will sometimes do. But in general, you can step through the code and such. And we would like to have, we don't have it yet, but on the platform, we would like it so they could upload the debug as well to the platform. And then they could essentially debug on the platform without keeping that stuff local as well, so that other members on the team could do this. That's in our plans as well. But yeah.
Really cool. Simon, you have a hand up?
Yeah, just wanted to add, Unity now also allows for dynamically expanding the memory. It just handles all that itself. So just wanted to answer that part of the question. And as a follow-up thing, will WebGPU handle memory allocation in the same way? Like I think at the moment you have to have a continuous block of memory. So even if you expand it, it has to like create a whole new block of memory. And sometimes obviously people have 150,000 tabs open with using up all the memory. I'm just wondering whether that will be alleviated in any way with the new systems.
No, so WebGPU has a different memory mechanism compared to WebAssembly. It's much more similar to WebGL. The two kinds of memory allocation essentially you can do are buffers and textures, and you just give it a size. But due to how GPUs work, etc., like you can't grow this thing. Basically, WebAssembly can grow memory because it has good control over the virtual memory mapping. GPU APIs just don't let us do that. I'm thinking of hacks with sparse stuff, but let's not get in there. But anyways, like, so the point is, we cannot control the virtual memory, and so we cannot grow resources. If you have to resize a buffer, then you need to create a new one and like copy the data, and etc.
Okay, good answers to this. One more question for Wonder. Does the Wonder Interactive platform support use cases for PWAs with offline first?
Yep, that's one of our initial goals that we put a lot of effort into, because we have people that are interested in running these things. There is no internet connectivity or where it's spotty. So PWAs are supported and offline is supported. Although not on the Space Lancers. We actually don't have a demo up with that yet, but it is available.
I believe next question is for you, Ken. Any thoughts on WebP versus Basis?
Well, I can take a first crack at this, but perhaps the Wonder Interactive folks should as well. So the main advantage of using Basis Universal is that you basically get the size of a JPEG, but the efficiency of compressed textures on the GPU, which is like a 4x improvement on the virtual memory that your textures take. So basically, if you're doing any kind of offline content, offline processing of your texture assets, you should always use Basis Universal. Turn up the quality to the highest possible. No worries about that. But you will get a huge VRAM savings and hopefully, minimal quality degradation by the use of the compressed texture extensions. And I mean, it provides universal compressed texture support. So you compress your textures once, and they work on desktop and mobile, which is once again a factor of 2 improvements on the number of asset bundles that you have to create for your game or your application. So basically, I'm a strong advocate of investigating and using Basis Universal and their tool chains. Any other comments?
Yeah, I'll just agree with that. Yeah, if you're cooking stuff up front, then yeah, you should use Basis in the browser. If you're doing things at runtime, then there might be a place for WebP or JPEG XL or one of these other formats. But yeah, if you get the chance or the opportunity to cook up front, then Basis is where to go on the browser right now. It's what to use.
Okay, so what looks like the last question for today: when will Chrome finally get a GPU debugger? Spectre.js is stagnant, and using native for browser stuff mixed with browser's own calls isn't fun. So first, I'm going to dispute the fact that Spectre.js is stagnant. We work with the Babylon.js and Spectre.js folks all the time, and improvements are made there on a consistent basis. And Corentin, can you attest to the fact that there's a WebGPU version of Spectre under development?
Well, so I don't know if Sebastian would like me to say that, but yes, like we're thinking of making a WebGPU version. It would be radically different and a complete rewrite due to the structure of the API, but it would also be better where Spectre.js is a thing where you can see the list of functions and it does a capture every time. This would be more like a render doc-ish potentially. So anyways, the thing is, both Sebastian and I have very limited bandwidth to work on this, and like shipping WebGPU and Babylon on WebGPU is like our topmost priority respectively. Hopefully at some point we can dedicate time to do this, and like contributions welcome, of course. Maybe you can also convince my boss to let me work on this a little bit, but we'll see. I don't think any of the browser implementers has time to do this before WebGPU v1. It's just like every additional thing at this point is just delaying the release, and I think nobody wants that. But also everybody wants everything, and we want the debugger as well. So it's just like hard prioritization, and I'm sure it will get done at some point, but without additional like engineering going into it, it's not going to be anytime soon.
Well, Corentin, I'm sure that your boss would be glad to give you the time to work on WebGPU debugging, so no worries there. In fact, I think we can maybe have a broader based effort among the entire team. All right, so I'm going to call that answered. Thanks for the question, and I think we should wrap up at this point. Thank you all for your great questions and participation here today. Jeff, do you want to wrap us up?
Yes, thank you to all the presenters. We greatly appreciate your time and effort. As a reminder, a recording of this presentation along with the slides will be available on the Kronos Group website, and a direct link will be sent to you in a follow-up email. As you leave the meetup, please take a moment to fill out the survey that pops up. Your feedback is important to us, and it helps us improve these presentations. Please let us know if there are any other Kronos-related topics you may be interested in, and thank you for joining us. We hope you enjoyed the meetup and have a great day.
All right, bye.
Thanks, guys.
Thanks, guys.